All right, so first off, as we convert this into Newton's notation, it'll always become a limit as n approaches infinity, and it's always going to be a sum from k equals 1. Wow, that summation looks terrible. Still looks terrible. From k equals 1 to n of what? It should be 2x sub k plus 2 times our delta x value. And so yesterday, I think I mentioned that delta x is always going to be equal to what? Yep, b minus a over n. So delta x is always b minus a over n. It's just the length of each subinterval that we draw these rectangles in. So in this case, that's 3 minus 0 over n, or 3 over n. And our x sub k value will always be equal to a, our lower limit, plus k times delta x. And so in this case, our a is 0, and then our k times our delta x just becomes 3k over n. So just 3k over n. Everybody good with that? Okay, so this ends up becoming the limit as n approaches infinity of the sum from k equals 1 to n of 2 times our x sub k, which was 3k over n, plus 2 times our delta x, which is 3 over n. Good or no? And then it's just a matter of simplification. So this becomes 6k over n plus 2 times our 3 over n and this becomes 18k over n squared plus 6 over n. Everyone good with that? And then for summations, one thing that we need to know about summations is that if we have a summation of one thing plus another thing, we can separate those summations out. And so that's something that we will talk about eventually. A lot more in depth when we do series, but it's just like with limits and derivatives and integrals. If you have an addition within it, you can separate it into two separate ones. So the 18 over n squared can be pulled out front because that's a constant, and we're left with a k. And then the 6 over n we can pull out if we want and just make it a summation of 1, or we can make it a summation of just 6 if we want by pulling out the 1 over n. And so if we add up all of the k's from k equals 1 to n, we need to remember that that's equal to n times n plus 1 over 2. So this is 18 over n squared times n plus 1 over 2. And then if we add up all of the 6's from the first 6 to the last 6, so 6 plus 6 plus 6 plus 6 n times, that ought to just become 6n. So we end up with 6n over n. And now it's just a limit of a rational function plus another rational function. So this becomes the limit as n approaches infinity of 18n squared plus 18n over 2n squared plus 6. And so this limit is 9 plus the 6 gives us 15. Good or no? And a bit more work than just taking the integral of it, right? And getting x squared plus 2x, evaluating that at 3 and 0 and finding the difference, which is also 15. But this is how the work was originally done by Newton. The summation of a constant is 0? No, the summation of a constant is not 0. So we summed a bunch of 6's together. We summed in 6's together. So the summation of that becomes 6n. So let me put a new page in here. If I say sum together from k equals 1 to 5, 7, right? That just means 7 plus 7 plus 7 plus 7 plus 7. It means 5 sevens, right? So if I'm asking for the sum from k equals 1 to n of 7, that's just n sevens, 7n. Does that make sense? Yeah, so that's what I did here. I pulled the 1 over n out, and I said I'm just summing together 6's now. And so if I sum together n 6's, that's 6n times the 1 over n is 6n over n. Our n's cancel to give us the 6. Everyone good? Any questions on that? All right, you guys want to try and do this one? Why did I pull the 1 over n out? The 1 over n, normally we pull out anything that's the same as what we're going towards at the end. So like if I have a 1 over, or if I have an n in there, I'll try and pull the n out. I don't have to pull the n out. It just makes it a little bit cleaner to look at normally. So if I left that in there, I'm just summing together a bunch of 6 over n's n times, which is still just 6 over n times n. You can leave it in there. It's not necessary to pull it out, but I figured since I was pulling out the 18 over n squared on the other one to just get a k here so that I have a formula I know, might as well pull the other stuff that's a little bit of a mess out of that one. Delphine. Yeah, not necessary. But, I mean, even, taking the 18 over n squared out is not necessary either. It just, it just gets thrown right back in immediately afterwards. But just to see this k, I think is helpful. And know that that's n times n plus 1 over 2. All right, so let's take, I don't know, what do you think it'll take? 2 to 3 minutes for you guys to work through this one? Give you a minute or two and see what you can do with it. Apparently, I forgot to resume the recording when I paused it for you guys to do that work. I don't know. So, just going to show that. And then we went through that one also when I forgot to start recording. So there it is for people that want to relook at it in the video later. All right, last one of these that we're going to do. There's an assignment on these also, so you can get more practice with it if you need to. But we'll do one more. Delta x ought to be 1 over n, and x sub k ought to be 1 plus k over n. And so we end up with a limit as n approaches infinity of the sum from k equals 1 to n of 1 minus 6 times 1 plus k over n squared times 1 over n. And simplifying that out, it is going to give us a whole big mess here. 1 minus, let's see, 1 plus k over n squared ought to be a 1 to start, so that's going to be 6 times the 1. And then we're going to have a 2k over n in the middle, so minus 12k over n when we distribute that. And then a k squared over n squared, and so minus 6k squared over n squared. And that's all times 1 over n. So we distribute all that through. The 1 minus the 6 is -5, so we got -5 over n, and then That becomes plus 12k over n squared and plus 6k squared over n cubed.
Today,
There's parentheses there on both sides now. I just forgot to put my closed parenthesis. Did I already distribute the negative? I did distribute the negative. Oh, man. Except I didn't distribute. Yeah, geez. I am struggling today. Like basic algebra, I can't even do. Okay. All right. Does that look better to everybody? All right. Sorry, I don't know. I don't know what's happening with my ability to do algebra today. I made more mistakes today than I made like all of last school year. So negative 5 over n, as we sum from k equals 1 to n, just becomes negative 5n over n. This one becomes minus 12n times n plus 1 over 2n squared, and minus 6 times n plus 1 times 2n plus 1 over 6n cubed. And so we end up with negative 5 minus 6. And what is that? Minus 2. Negative 13. Everybody good there or no? Hopefully you all get the idea with this, and hopefully you can all do algebra better than I've done algebra today. Yeah? I hope so. All right. A couple of quick things to talk about before we actually start taking integrals for real, which I know you know how to do, but we'll get through the majority of those just regular integrals today, I hope. If we're talking about integrals, and we talk about area, and area is always positive, right? So if I talk about what's the area underneath this curve, that's not what this question is asking, but if I ask what's the area underneath this curve, it's talking about the area between the curve and the x-axis. So the area would be 1 and 2, right? Our area should just be 3. But if we talk about the integral, whenever we talk about integrals, anything that's below the x-axis comes out to be negative. So it should be 2 and then minus 1. So the integral here should equal 1, whereas the area itself is 3 units squared. So hopefully you all remember that area under the curve is always going to be a positive value, and that anything that we talk about when we talk about the integral, above is positive and below is negative. Everybody good with that? All right. And then the next thing is, how do we find the average value of a continuous function? This is the mean value theorem for integrals. So the average value of a function, of a continuous function on an interval, is just the value of h, we'll call it h, height, so that if I make a rectangle out of b minus a and h, right, I have this length from a to b and this height from the x-axis to h, where that area of that rectangle would be equal to the area underneath the curve. Right. So what we're effectively saying here is that the integral from a to b of f of x dx needs to equal the area of this rectangle, which is b minus a times h. And so the average value h is equal to 1 over b minus a times the integral from a to b of f of x dx. That should seem very familiar. This is the mean value theorem for integrals. Should all have heard of that before. But for some reason, if you've forgotten, this is the formula for the average value of a continuous function. And so that, remember that one problem that was on the multiple choice that I said I wasn't going to grade? I think it was number 3. It asked for the average value of the function. And when I put that together, I misread it as the average rate of change of it. So we make sure that you don't do what I did and misread average rate of change for average value. And that's actually what most of you did, is I think it's found the average rate of change. And only like 1 or 2 people actually used this formula and got the actual average value of the function. I didn't grade it because we hadn't talked about it, because I shouldn't have put that problem on there. But make sure that if it asks for the average value of a function, you use the mean value theorem for integrals. So let's, there it is, look at that. The mean value theorem for integrals. So let's do that here real quick. I know you guys all know how to take the integral of 1 over x. What's the integral of 1 over x? Yeah, natural log of the absolute value of x, right? Plus a constant, that's right, if we're not doing a definite integral, it's an indefinite integral. So in order to find the average value of 1 over x on the interval from e to 2e, first off, we want to note that this is a continuous function. This is continuous on 0 to infinity, which e to 2e is included on that, right? So it's a continuous function, so therefore we can find the average value, we can find the mean value. It should be equal to 1 over 2e minus e times the integral from e to 2e of 1 over x dx. 1 over 2e minus e is just e, right? So 1 over e, and then the integral of 1 over x, like you guys just said, was natural log absolute value of x, evaluated from e to 2e. And we'll talk all about, I'm not going to talk about all the rules and how they get derived for ones that we should already know, but I'll send out the formula sheet. But you should know that formula. And you should know the second part of the fundamental theorem of calculus, which says that if we have upper and lower limits, we just evaluated it. So 1 over e times natural log of 2e minus natural log of e. I didn't bother with the absolute value anymore because both 2e and e are positive values. So it's just a little redundant. Natural log of 2e is the same as what? I see somebody has said 2, and somebody has said natural log of 2. Anybody else care to weigh in? Because neither of those are what the natural log of 2e is equal to. Yeah, Darius, you got it. The natural log of 2 plus 1. So this becomes natural log of 2 plus natural log of e, right? The rules for logarithms say if you have multiplication within the argument of the logarithm, you can separate into 2 separate logarithms using addition. So natural log of 2 plus natural log of e minus your natural log of e. And natural log of e is 1. minus 1 cancels out. So you end up with natural log of 2 over e is your final answer, or the average value of 1 over x on that interval. Everybody good with that or no? So that's the y value, and we would say that it occurs at, well, natural log of 2 over e equals 1 over x. That'd be at x equals e over ln 2. So the average value is natural log of 2 over e, and it occurs at e over the natural log of 2. Good or no? All right, so we are now going to talk quickly about the first and second parts of the fundamental theorem of calculus after I go and that's the dog that's banging at the back door. Because, oh, never mind, my kid is doing it. I don't have to. Perfect. So the fundamental theorem of calculus. The first part of the fundamental theorem of calculus basically just says that the derivative of the integral of a function from a constant to x is equal to the original function. Right? So if we say that capital F of x is the integral from a, some constant a, to x of another function, well then the derivative of capital F is just the derivative of that integral, and it should just go back to our original function in terms of x. Right? So the first part of the fundamental theorem of calculus is just saying the derivative and the integral are inverse operations of each other. That if you take the derivative of the integral from a constant to x, you just get the original function. Everybody good with that? I hope. Should seem familiar. So these start out very easy. If I want to know what's the derivative of the integral from a constant, negative pi, to x of a function, it should just be a function in terms of that variable. Easy or no? Everybody okay with that or no? What should the bottom one become? The lower limit of a does not matter at all, Darius. That's correct, as long as it's a constant. And you can think about it this way. So we know what the integral of cosine is, right? What's the integral of cosine? What's the integral of cosine? Not negative sine, sine, right? So what this is effectively doing is saying take the derivative of the integral of cosine from negative pi to x. So this is saying take the derivative of sine evaluated at x minus sine evaluated at negative pi. Okay. Well, what's the derivative of sine of x? It's cosine x, and then this whole piece right here, this is just a constant, right? Sine of negative pi is a constant. So cosine x minus 0, or just cosine x. It's the same thing here. What's the actual integral of this function? Yeah, it's inverse tangent, right? So effectively, this becomes the derivative of the inverse tangent evaluated at x minus the inverse tangent evaluated at 0. And inverse tangent evaluated at 0 is just a constant. I mean, it happens to be 0, but it's just a constant, right? And so the derivative of inverse tangent of x is 1 over 1 plus x squared. And so that second piece of it, as long as that lower limit's always constant, that second piece of it always gets canceled out when you retake the derivative of it. They like to ask a question or two with these. Usually they aren't a constant to just x. They're something a little bit more complicated, like a constant to a function, perhaps. So like 1 to x squared. So if we were to try and work through this one in that same manner, we want to find the derivative of this. Well, that'd be the derivative. And like we said, what's the integral of cosine? It's sine, right? So we'll say sine of t evaluated from 1 to x squared. So that becomes the derivative of the sine of x squared minus the sine of 1. And the sine of 1 is just what? Sine of 1 is just a constant, right? So when I take the derivative of a constant, it becomes 0. The derivative of sine of x squared is just 2x sine of x squared. So in this case, because we had another function up there, we have to use the chain rule when we do the differentiation part. Sometimes I'll write this out as let's convert this into an integral from 0 to u of e to the t squared dt, and take the derivative with respect to x of that. That doesn't really look like u there, but with u equal to x squared, right? And so then when we integrate this from 0 to u, well, we probably don't know what the integral of e to the t squared is off the top of our head, so we won't really be able to use this exact same method here, but we know that when we integrate it and then plug it in, we should get e to the u, and we should get whatever the integral of e to the t squared is, and then we're going to evaluate the derivative of that at u, so that just becomes e to the u. And then the second piece of it is just a constant, and we have to multiply that by the derivative of u. So 2x e to the x squared. Does that make sense? It's not u squared, or sorry, it's not e to the u squared because we let, oh, sorry, oh, it was t squared, huh? My mistake. Man, I am having some trouble here. Yeah. And so this should be x squared squared. Yeah. And yeah, I don't know. Yeah, we took the derivative of the sine and I kept it as sine. That should be cosine. Man, it's been a rough day today. All right, everybody, even with my inadequacies on algebra today, everybody good with that or no? All right, seems like you guys are doing better with it than I am. So what about this one, where we have an integral from x to 5 of 3t sine t dt? What do we need to do with that one? Yeah, just use the fact that we can make this the opposite of the integral from 5 to x of 3t sine of t dt. And then we're taking the derivative with respect to x of that, which should become negative 3x sine x. I think I finally did that one right, huh? So remember, you can use that rule if you need to. flip the limits. Everybody good there? All right, and then one more here, I think, where we've got a function as the lower limit and a function as the upper limit. And so how can we deal with that? Yeah, we can make it a subtraction. So choose any constant. We can call this now the integral from 0 to x squared of 1 over 2 plus e to the t dt minus the integral from 0 to 2x of 1 over 2 plus e to the t dt. It doesn't matter what constant you choose. Any constant is fine. And then we're going to take the derivative of this with respect to x. And what does that end up giving us? For the first one, we should have a 1 over 2 plus e to the x squared times the derivative of the x squared, so 2x over 2 plus e to the x squared, and then minus 2 over 2 plus e to the 2x. Good or no? And we should note that basically all we're doing here is we're taking the derivative of the x squared and multiplying that by this function with x squared replacing the t. And then subtracting the lower limit, right? Derivative of 2x, so 2, and then over the 2 plus e to the 2x. Any questions or issues with that? I always like to put like one question like that on the AP test. All right, and then we've already been using this, but the second part of the fundamental theorem of calculus is just the evaluation part, that if we have an integral from a to b of a function, it's just the integral of the function evaluated at b minus the integral of the function evaluated at a. So we've done that a bunch already at the beginning of this, and we did that with our average value one. So I'm pretty sure you guys all know and remember how to evaluate an integral. Yeah? All right, so let's see if we can remember how to integrate stuff. What's the integral of 5 dx? The indefinite integral of 5 dx. No, Adrian, it's not 5x. Thank you. 5x plus a constant. What about 2x cubed? Should go up to the 4th power, divide by 4, so that should become 1/2 x to the 4th plus our constant. Everybody good with that? Don't forget plus c. Yes, Adrian, I can go back a slide for a second. Let me know when you're ready. All right. So 1 over x to the 5th, that's the same as the integral of x to the -5, right? So we'll go up to x to the -4, and then divide by the -4. So what should that give us? Should be -1 over 4x to the 4th. plus our constant. And still works for rational powers. X to the 3/4 should become what? X to the 7/4 divided by 7/4. So 4/7 x to the 7/4 plus our constant. Everybody good there? All right, what about tangent x over secant x? I have no room here, so I'm gonna make a new page for this. So the integral of tangent x over secant x. What should we do with that first? Yeah, just simplify it down. Right, this is the same as the integral of sine cosine over 1 over cosine, which is the integral of sine. And what's the integral of sine? Negative cosine x plus our constant. Good or no? Let's see, this one will probably fit here just fine. Integral of 5x cubed should be 5/4 x to the 4th. And the integral of cosine, which we've done multiple times now today, is just sine plus our constant. And then what about 8t cubed minus 6 root t plus 1 over t cubed? What should that become? 2t to the 4th. And this is 6t to the 1/2, right? So that goes up to t to the 3/2. And if we divide by 3/2, that's the same as multiplying the 6 by 2/3. And 6 times 2/3 is 4. And then this is plus t to the -3, so we'll go up to t to the -2 and divide by the -2. So minus 1 over 2 t squared plus our constant. Good or no? What about the integral of 1 over cosine u cotangent u? We don't see an immediate, nice, easy integral with our trig functions. We should try to rewrite them. So what is this the same as? This is the same as the integral of secant u tangent u du. And what's the integral of secant u tangent u du? Should be secant u plus a constant. And what about x squared minus 1 squared over x squared? How are we going to deal with that one? Okay, expand out the top. Alice, that's the right idea. Substitution is going to be a little bit of an issue with this one, Adrian. So we're going to expand out the top. That becomes an integral of x to the 4th minus 2x squared plus 1 over x squared. And then what are we going to do, Alice? Yep, divide x to the 4th by x squared, 2x squared by x squared, and 1 by x squared. So we've got x squared minus 2 plus x to the -2. Everybody good with that? Which should give us x cubed over 3 minus 2x, and then up to -1 and divide by -1, so minus 1 over x plus our constant. Any issues with that? Everybody okay with that? I may not be able to do algebra today, but at least I can still take an integral. All right, you guys do these 4 right here. I'll give you a minute to do these 4. Ready, go. All right, what's the first one? 1 over x plus our constant. What's the second one? Should be 3/5 x to the 5th. And then that should go up to -2. We divide by the -2 to cancel that out. So plus 1 over x squared plus tangent x plus our constant. Next one is just inverse tangent, right? That's just inverse tangent of u plus a constant. And in this last one, 2e to the x just becomes 2e to the x plus secant x. And then the integral of x to the 1/2 ought to be minus 2/3 x to the 3/2 plus the constant. Any issues with those? All right. Should we stop there, or you guys want to continue on and evaluate a couple of these? Sure. All right. Let's evaluate the integral from -1 to 3 of x cubed plus 1 using the second part of the fundamental theorem of calculus. The integral of x cubed plus 1 is x to the 4th over 4 plus x. And then we're going to evaluate from -1 to 3. So that should become 3 to the 4th, which is 81 fourths plus 3, minus -1 to the 4th, which is 1, and 1/4 minus 1, which ought to give us what? 24. All right, I think we'll stop on this one. When we start talking about the area stuff, things start to get a little bit more complicated, especially for functions that cross through the x-axis. So we'll deal with this one tomorrow and finish up this stuff, or not tomorrow, I guess, Monday, and then finish up all the basic integral stuff so that we can get into the more complicated stuff early next week. Any questions on anything?